Hello, today we're going to be talking about Hess's law and thermochemical reactions and stoichiometry. So that's what I'll be talking about today. Follow along the PowerPoints. And after the PowerPoints today, there'll be a daily homework for you to complete on Blackboard. So today we'll start off by talking about the stoichiometry of thermochemical equations. So again, when you look at a thermochemical equation, you need to make sure it's a balanced equation, because in order to get the right mole-to-mole ratios, you need to have a balanced chemical equation. So that's the first step you need to do. So a balanced chemical equation. Now there are two things about thermochemical equations. It's the sign of delta H for the reaction. So if it's negative, it's an exothermic reaction, and if it's positive, it's endothermic. So if in one direction the reaction is endothermic, such as in this reaction, so this direction it's endothermic, the reverse reaction would be exothermic. So if I was to write this reaction in reverse, so I say 2H2 plus O2 gives me 2H2O. Delta H would equal negative 572 kilojoules. So again, whenever you reverse a reaction, you just flip the sign of delta H. So that's one thing you can do to thermochemical equations is if one direction is endothermic, the reverse direction is exothermic. Secondly, delta H is proportional to the coefficients in front of the reactants and products. So in the number 2, we see here that 1 mole of hydrogen gas that reacts with O2 produces 286 kilojoules of heat. Whereas for every 1/2 mole of O2 that reacts, it produces 286 kilojoules of heat. For every 1 mole of water that is produced, we produce 286 kilojoules of heat. So the coefficients in front of the reactants and products tell you the number of moles is needed to produce the amount of heat given in the delta H, because delta H again is kilojoules per mole. Now, two key things you need to remember with thermochemical equations is that sometimes when you're balancing the coefficients, it may have to use fractions, because when they want to use fractions is because one of the reactants and products needs to have 1 mole, 1 as a coefficient. So for example, in this reaction of sulfur and oxygen to produce SO2, we put a 1/8 in front of S8 so that there's a 1 in front of O2 and a 1 in front of SO2. So that means for every 1 mole of O2 that is reacted, we produce 296.8 kilojoules of heat. For every 1 mole of SO2 that we produce, or we produce 296.8 kilojoules of heat. So don't be alarmed if you see fractions as coefficients. Typically they do this when they want one of the reactants or products to have a coefficient of 1. The second thing to remember is that the equivalence to the coefficient and the delta H. So in that sulfur reaction, for every 1/8 mole of sulfur, we produce 296.8 kilojoules of heat. Now, if we want to know how much 1 mole of sulfur would produce, so 1 mole of S8, and apologize, there's no subscripts on the on this template. So if we want to know what 1 mole of S8 is, we just take 8 times 296.8. And the reason we multiply by 8 is because 8 times 1/8 would give us how much 1 mole is. So again, 1/8 of a mole produces 296.8 kilojoules. So we multiplied by 8, we would get the number of kilojoules of heat that is produced when we do 1 mole of S8. So it's about 2,374 kilojoules. Now we look at this reaction here. For every half mole of O2 that is consumed, we produce 286 kilojoules of heat. So if we wanted to know what 1 mole of O2, how much heat 1 mole of O2 would produce, we would need to multiply it by 2. So here 1 mole of O2 would be 2 times 286. So it would be 572 kilojoules of heat produced. So again, that's how you use the coefficients to determine how much heat is produced for that particular reactant or product. Now we're going to use this information, and remember that delta H equals Q of reaction divided by N, where N is the number of moles. So remember this equation here when we're doing stoichiometry involving thermochemical equations. Delta H equals Q of reaction divided by N. So now we're going to look at a few examples involving thermochemical stoichiometry problems. So here we have an example. We're looking at a reaction involving propane and oxygen. It says we have a tank that contains 3.56 kilograms of oxygen gas. Calculate the heat associated with the complete combustion of all the oxygen gas in the tank. And one of the first things you need always for stoichiometry is to have a balanced chemical equation, which is what's given here. So in this equation, which is balanced, we know that the delta H of reaction is negative 2,044 kilojoules. So it's exothermic. Delta H is negative. And we know that for every 1 mole of propane that combusts, we produce this much heat. For 5 moles of O2 that combust, this much heat is produced. For 3 moles of CO2 that is produced, this much heat is released. And for 4 moles of steam that is produced, again, we produce 2,044 kilojoules of heat. So now some important things here. What we're looking for is the heat. So it's given us the amount of gas, oxygen gas. It's given us the delta H. So again, it's given us the amount of oxygen gas, 3.56 kilograms, and it's given us the delta H, negative 2,044 kilojoules. And we know that for every 5 moles of O2, we produce 2,044 kilojoules of heat. So what do we know? We know that for every 1 mole of O2, we take the delta H and divide it by 5 moles of O2, we get the amount of heat that is produced by 1 mole of O2. Because again, 5 moles of O2 produce this much heat. We want to know how much heat is produced from 1 mole of O2. So the way we do that is we take the 2,044 kilojoules divided by 5, which is the coefficient of that reactant, and we get how much heat is produced from 1 mole of O2. Again, when we're doing this problem, we need to make sure amount is in moles. So right now we have 3.56 kilograms of oxygen gas. One of the next steps would be to convert that to moles. So we take the grams of O2, make sure you convert it to grams, this is in kilograms, convert it to moles of O2, and then to heat. And again, remember that to go from mass to moles, moles equals mass divided by molar mass. And for Q equals delta H times N. So for step 1, we convert the kilograms to grams. And again, this should be oxygen, it's not propane. Let me make that correction here. So this should be oxygen. So that's O2. So we have 3,560 grams of O2. Now we can take the mass of O2, convert it to moles. So we have 111.25 moles of O2. Now notice this is bigger than 1, so our answer should be greater than 408 kilojoules because 1 mole of O2 produces 408.8 kilojoules. And we have 111.25 moles of O2, so this is going to produce a lot more heat than just 1 mole. And so to find the heat, again, we take the moles times the delta H, we get the amount of heat produced. So about 45,500 kilojoules of heat is produced from this reaction. So again, remember Q equals delta H times N. So now let's do another example. And so in this example, again, we have another combustion reaction, which is exothermic. And we want to know how much butane is consumed when we have a combustion reaction that produces 18,500 kilojoules of heat. So in this problem, again, we want to know how much butane in grams is consumed when we do this combustion reaction. And so what we know from this balanced chemical equation is that 1 mole of butane produces 2,658 kilojoules of heat. So again, 1 mole of butane produces 2,658 kilojoules of heat, and we want to know how much butane is needed to produce 18,500 kilojoules of heat. Now remember here that 18,500 is a lot bigger than 2,658. So the amount of butane that's needed is going to be more than 1 mole. So remember from our equation, Q equals delta H times N. So in order to know the amount of heat or the amount of butane that is used, we have to rearrange this equation, and N, which is moles, equals Q divided by delta H. So if we know the Q, we know the delta H, we can find the number of moles. And so it says 18,500 kilojoules of heat is produced. That means it's negative, so negative 18,500 divided by the delta H, which is negative 2,658. and we get about 6.96 moles of butane. So now we know the moles of butane. We can determine the mass of butane. So the mass equals moles times molar mass. And so this would be 6.96 times the molar mass of butane is 58. And that gives us 404 grams of butane were consumed. So again, we were looking for how much butane in grams. So the first thing we need to do is find N, because N equals Q divided by delta H. The fact that it says produces means the Q is negative, delta H is negative. We get the moles of butane. From the moles of butane, we can get the mass of butane. I'll pause here for just a few seconds so you can see this, and then we'll move on to the next example. Now, in our second example of this thermochemical stoichiometry, we want to know how much heat is released. How much heat is released with 550 grams of CO2 are produced. So we want to determine how much heat is produced or released when we have 550 grams of CO2 produced. Again, it gives us the delta H of this reaction, which is negative because it's a combustion reaction. All combustion reactions are exothermic. And so what we know is that 5 moles of CO2 produces 4,700 kilojoules of heat. So we know 5 moles. Well, before that, how much heat? Remember, Q equals delta H times N. So we know the delta H, which is given to us, is 4,700 kilojoules per mole. We need to find N, which we can find from the 550 grams of CO2. Then we can find Q. Now here from the balanced equation, 5 moles of CO2 is equal to 4,700 kilojoules of heat. So for 1 mole of CO2, that would be taking the delta H and dividing it by 5. So it's about 940 kilojoules. So 1 mole of CO2 produces about 940 kilojoules of heat. So now we have the delta H in reference to 1 mole of CO2. We need to find N. So N is equal to mass divided by molar mass. So the mass here is 550 divided by the molar mass of CO2, which is 44, and we get the moles of CO2. So 12.5 moles. So now we have the moles. We have the delta H. We can determine Q. So Q equals delta H negative 940 times 12.5. It was about 11,750 kilojoules. Now you can answer with the negative sign or without the negative sign because it says how much is produced, so it's already understood that the reaction is exothermic. So I'll give you a few minutes to digest this example and we'll move on to the next one. So this is kind of a conclusion of thermochemical stoichiometry problems. Now we're going to look at a way to determine delta H. So if you remember when we first started chapter 6, we talked about delta H, which was a state function. As we said here, delta H is equal to Q divided by N. But there are also two additional ways you can calculate delta H. Because it's a state function, it doesn't depend on the path. So one way we're going to use to determine delta H is called Hess's law. And that's what we're going to talk about next in this lecture is Hess's law. How do we use Hess's law to determine the delta H of a chemical equation? So for Hess's law, as I said, it doesn't matter what path you take to determine enthalpy. Since enthalpy is a state function, it's always going to be the same. It doesn't depend on the path, just the initial and final state. But before we actually delve into a Hess law problem, let's talk about a few things you can do to manipulate chemical equations for Hess's law. So for example, we have this reaction. Ozone decomposes into O2. It's an exothermic reaction. One thing we can do to this is we can multiply it by a coefficient. So let's say instead of 1 mole of ozone, we want to know how much 2 moles of ozone, how much heat 2 moles of ozone would produce. So what we do is we multiply the whole equation and the delta H by 2. And so now we'll know how much heat is produced when we have 2 moles of ozone that are decomposed. So that's one thing you can do to a chemical equation is you can multiply by a coefficient. I apologize if any of my spelling is off. Yeah, I don't have word check on this. So that's one thing you can do. You can multiply by a coefficient just like we did here. We found out how much heat is produced from 2 moles of ozone. Another thing you can do is you can flip the reaction. So in the forward reaction, notice it was exothermic. If we flip the reaction, so now the products become reactants, the reactants become products, you just change the sign of delta H. So if the forward reaction is, if one direction is exothermic, the opposite direction is endothermic. And so this is another thing you can do to thermochemical equations is you can flip the equation. And what we mean by that is that the products become reactants, the reactants become products. Look at another example. So here we have the vaporization of water. So for every 1 mole of water, we need 88 kilojoules. So this is an endothermic reaction. So 1 mole of water to vaporize it needs 88 kilojoules. If we want to know what 3 moles of water, then we multiply the whole reaction by 3, including delta H. So now you see delta H is increased by a factor of 3. So we took 3 times 88, we get 264. Now if we flip the reaction, so now we want to know how much heat is released when when steam condenses into water, you see that we change the sign of delta H. So for condensation, it's exothermic. For vaporization, it's endothermic. So again, from this, you should gather that two things we can do to a chemical reaction is we can multiply it by a coefficient, which means you also multiply the delta H, and you can flip the equation, which changes the sign of delta H. These are the two operations you can do with Hess's law. Now let's look at an example. So here we've been given this information. So typically with Hess's law problems, you'll be given a series of chemical equations where the delta H is known. And what you have to do is rearrange them so that when you add them together, you get the delta H, the equation that you want to know the delta H for. So we want to know the delta H for this reaction here. And we're given these two equations. So we have to rearrange these equations in order to so that when we add them together, we get this equation. So this is the equation we want. The 3H2 plus ozone yields 3H2O. So the first thing we want to do is make sure the reactants and products are on the same sides of the equation and the equation we want. So we take a look here. We see H2 is a reactant, O3 is a reactant, and H2O is a product. So in the equation with H2 and H2O, H2 is a reactant, check. H2O is a product, check. So we don't need to flip the first reaction. Now we see here ozone in the equation we want is a reactant. However, ozone in the equation we have is a product. So what we do next is we flip the equation to make ozone a reactant. And when we flip it, we change the sign of delta H. So now delta H becomes negative. So now that the reactants and products are on the correct side of the equation, the next step is to determine the correct coefficients. First step is to make sure reactants and products are on the correct side of the chemical equation. Second step, we got to determine the correct coefficients for the reactants and products. So what we notice here is in the equation we want, we have 3H2O, 1O3, and 3H2O. In the equations that we have 2H2, 1O2, and 2H2O, excuse me. So you notice that the coefficients of H2 don't match. So we need to multiply something by 2 so that we can get a coefficient of 3. So in order to turn 2 into 3, what do you have to multiply by? That's correct, 3/2. So what we're going to do is we're going to multiply the top equation by 3/2 to get the new coefficients. So when we multiply the top equation by 3/2, that includes the delta H as well. It has to be multiplied by 3/2. So when we do that, now you'll notice that 3 is the coefficient of H2, 3 is the coefficient of H2O, and we have a new delta H here as well. But don't worry about the 3/2 O2. If you do it correctly, these will cancel each other out. Now if we go to ozone, and the equation we have for ozone has a coefficient of 2, and the equation we want for the equation that we want, ozone has a coefficient of 1. So we need to turn 2 into 1. So how do we do that? That's correct. We multiply by 1/2. So we need to multiply the entire equation, not just the equation. Got to multiply the equation and delta H. We multiply the entire thing, including delta H. Don't forget delta H. So when we do this, we now have ozone with a coefficient of 1, and the delta H has been multiplied by a half as well. And then we have 3/2 O2. So don't worry, we have 3/2 O2 on the reactant side, we have 3/2 O2 on the product side. We'll show you what happens to these. We'll just erase some of these lines so we don't get too confused. So now, how do we have the right coefficients? Reactants and products are on the right side of the equation. Now what we do is we cross out what's the same on both sides. So since we had 3/2 O2 on the reactant side, 3/2 O2 on the product side, they cancel each other out. You can cross them out. And so now what we do is we add the two equations together and we add the delta H's. Just 3H2, 1 ozone gives 3H2O, and we get our delta H by adding these two together. Again, this equation at the bottom has to be the same as the equation we want. And you just add the two delta H's. I'll give you a few seconds to kind of mull over this, and we'll go on to the next example. Okay. So now we have another Hess law example. So here we're given two equations where the delta H's are known, and we're asked to determine what's the delta H of this equation. So again, the first thing you want to do is, number one is make sure reactants and products are on the correct sides. So if we look here, P4O6 is a reactant in the equation we want. P4O6 is a product in the equation we have. So one of the first things we have to do is flip the top reaction to make P4O6 a reactant. P4O10 is a product. P4O10 in the equation we have is a product. So the first thing we need to do is flip the top equation, which is what we did. So you see here the sign has changed because we flipped the equation. P4O6 is now a reactant. So that's the first step. You make sure reactants and products are on the correct sides. Step number two is make sure you have the correct coefficients. So here, P4O6 has a coefficient of 1. P4O6 has a coefficient of 1. O2 has a coefficient of 2. If you notice here, we have 5 on the reactant side, 3 on the product side, so we're going to have a surplus of 2 on the reactant side. And P4O10 has a coefficient of 1. Notice that the P4s will cancel. So in this example, the coefficients are correct. So now we cross out what's the same on both sides. So the P4s cross out. And now we can add the two equations together. Again, when you add the two equations, you add the two delta H's together. And so notice we have an extra 2 moles of O2 on the reactant side, because 5 minus 3 is 2. And so this is the delta H of this chemical equation. Again, step one, make sure reactants and products are on the correct sides. Step 2, make sure you have the correct coefficients. Then you're going to cross out what's the same on both sides and then add the two equations, or in this case, two equations together. Now let's look at another example. So here we want to determine the delta H for this chemical equation, and we're given two equations where the delta H's are known. So again, what's the first step? That's right. You got to make sure the reactants and products are on the correct sides of the chemical equation. So here notice NOCl is a reactant, but in the equation given to us, NOCl is a product. So one of the first things we're going to have to do is flip the second equation to make NOCl a reactant. Secondly, notice that N2 and O2 are products in the equation that we want, but in the equation we have, they're reactants. So in this example, we have to flip both reactions. So we flip the top one. Now it goes from endo to exothermic. Notice NO is a reactant. And we flip the bottom one as well. So now notice NO, excuse me, not NO. Notice that NOCl is a reactant, and NOCl is a reactant in the equation we want. NO2 and O2 are products, and NO2 and O2 are products in the equation that we want. Cl2 is a product, Cl2 is a product. Notice that the NOs are going to cancel. So we got the, we got the reactants and products on the correct side. What's the second step? That's right. We got to determine the correct coefficients. So here we'll notice that N2 has a coefficient of 1/2, O2 has a coefficient of 1/2. But in the equation we want, N2 has a coefficient of 1, and O2 has a coefficient of 1. So how do we turn 1/2 into 1? That's right, we multiply by 2. So the top equation we're going to multiply by 2 to convert 1/2 into 1. You got to multiply the whole thing by 2, including delta H. Now for the second equation, we also have to multiply by 2 because here NOCl has a coefficient of 1, but in the equation we want, NOCl has a coefficient of 2. Cl2 in the equation we want has a coefficient of 1, and in the coefficient we have, it has a 1/2. So the second equation has to be multiplied by 2 as well to get the correct coefficients. So now we've multiplied both equations by 2. Just clean up the screen a little bit. So now we can cross out what's the same on both sides. And so in this case, the 2NO cross out. And now we can add the two equations together. And that means you add the delta H's as well. So moving on to the next example. Here we have 3 equations. Oops, let me go back. We have 3 equations that we need to determine, that are given to us to determine the delta H of this equation. So we want to know what the delta H is for the hydrogenation of ethene to ethane. And it's given us, in this case, 3 chemical equations. So again, we want to see what's the delta H when we hydrogenate ethene to ethane. And we got to use these 3 equations to rearrange them such that When we add them together, we get this equation. Now notice here, C2H4 is a reactant, and in the equation we want, C2H4 is a product. So that equation we don't have to flip. C2H4 is 3O2, oops, excuse me, plus 3O2 yields 2CO2 plus 2H2O. DH negative 1411. That one's good. Now in the second equation, we have C2H6. Now here notice C2H6 is a reactant, but in the equation we want, C2H6 is a product. So we're going to have to flip the second equation and change the sign of delta H. So we have 2CO2 plus 3H2O yields C2H6 plus 3.5 O2. Or we can just say 7/2. Makes it better. Now the delta H, we've got to change the sign. So delta H, negative 1560. Oh, excuse me, positive 1560. Got to keep the, got to change the sign. My bad, my bad. All right. Now if we go to the third equation, H2 is a reactant, and H2 is a reactant in the equation we want. So we don't have to flip the third equation. So we have H2 plus 1/2 O2 yields H2O. Delta H equals negative 285.8. So now that we've got all the reactants and products on the correct sides of the equation, we need to look at the coefficients. So here's C2H4 as a coefficient of 1. In the equation given to us, C2H4 is a coefficient of 1. H2 has a coefficient of 1. In the equation given to us, H2 has a coefficient of 1. C2H6 has a coefficient of 1. In the equation given to us, in the equation we want, C2H6 has a coefficient of 1. So we don't have to do anything with the coefficients. Now we got to see if these cancel out. So this 2CO2 cancels with this 2CO2. 3H2O cancel with these three H2Os. Now 7/2 O2 cancels with the 3O2 and the 1/2 O2. So now notice that when we add these together, we get C2H4 plus H2 yields C2H6 delta H equals, we got to add all those three delta H's together. Negative 136.8 kilojoules. So that's the delta H of this reaction. Give me a few seconds to look over it before I clear it. We'll look at one more example, and that'll conclude today's lecture over thermochemical stoichiometry and Hess's law. So in this example, we want to know what's the delta H of NH3 plus O2 gives us NO and H2O. And it's given us three equations to determine the delta H for this equation. Okay. So let's take a look at this one. So again, NH3 in the equation given to us, in the equation we want, excuse me, it's a reactant. In the equation given to us, it's a product. So one of the first things we're going to have to do is flip the second equation. NO is a product in the equation we want, and NO is a product in the equation we have. So we don't have to do anything to that equation. So far the one we have to flip is the second equation. Now H2O is a product in the equation we have. H2O is a product. So we don't need to flip that one. So let's go ahead and write. And again, O2 we didn't need to as well because O2 is a reactant, and in most of these, O2 are reactants. Both O2s are reactants. So now, the first equation we don't need to flip, so let me write that one out. The second equation we do need to flip. When we flip, we change the sign of delta H. The third equation, we don't need to flip. So now we have the reactants and products on the correct sides of the chemical equation. Now we got to work on coefficients. So for NO, NO has a coefficient of 2 in the equation we have. It has a coefficient of 4 in the equation we want. So the first thing we're going to have to do is multiply this equation by 2. I can draw 2. Boom. Now NH3 in the equation we have has a coefficient of 2. In the equation we want, it has a coefficient of 4. So we're also going to have to multiply the second equation by 2 as well. Now if we look at H2O, it has a coefficient of 2. In the equation we want, it has a coefficient of 6. In order to turn 2 into 6, we've got to multiply by what? That's correct, 3. Let me see if I can draw 3 freehands. That's not bad. So again, the first equation we're going to multiply by 2. Second equation we're going to multiply by 2. And the third equation we're going to multiply by 3. So this becomes 2 N2 plus 2O2 yields 4 NO. And DH is multiplied, or delta H, excuse me, is multiplied by 2. Do that with my calculator. There it is. 80.5 times 2. Okay. Now we go to the second reaction. We also multiply by 2, so 4 NH3 plus, let's see, the yields 2 N2 plus 6 H2. So DH is multiplied by 2 as well. 183, positive 183.6. That should be negative. Fix that. This should be negative. And this should be. Now the third equation we multiply by 3, 6H2 plus 3O2 yields 6H2O. DH is also multiplied by 3. It would be negative 1450. So now we have the right coefficients. We have everything on the right side. We can add the 3 equations together. Let's do some canceling out. So this 2 and 2 cancels with this 2 and 2. This 2O2 doesn't cancel. 6H2O, excuse me, 6H2 cancels with 6H2. So now we can add everything we have left. So we have 4NH3 plus 5O2 yields 4NO plus 6H2O. And DH, just add up those three. Negative 361 plus 183.6 minus 1451. Negative 1628. So that's the delta H of this reaction. So that concludes today's lecture on thermochemical equations and Hess's law. Make sure that you do the daily homework for today, which will be over these 2 topics, and it'll be due Thursday before class starts. I'll give you a few seconds to copy down any notes, and then I'm going to stop the session.